Good morning, friends. After the discussion of the some numerical of illustration, now the next topic is to obtain the differential equation. Now, what is the first the differential equation? The equation in this equation in which the terms are different order of derivative, like this way, this square y upon dt square plus dy by dt plus constant is equal to 0. That is known as the second order derivative equation or the second order differential equation. Up to a level of 11th and 12th standard, only in our syllabus, the second order differential equation. Now in college level, here third order, fourth order differential equation you are also going to study in college level. Okay. Now differential equation, that means the first term is double derivative of given function. Next term is single derivative plus constant equal to 0. This term of the equation is known as the differential equation. We are going to deal this type of the differential equation for pure simple harmonic oscillation. After that, the damped oscillation, and then the forced oscillation. We have the experience as we sit on the swing at home. So what's happened? Initially the swing is in equilibrium position. As we sit on a swing, what's happened? So slightly displaced from its equilibrium position. Actually, due to the seat on a swing, this swing is perform the oscillation for the long time. But we have the experience after the 5 or 10 oscillation, its displacement is going to decrease and at last it becomes the stop. What is the reason? Because the oscillation of this swing takes place in a medium. Therefore, a medium apply the resistive force on oscillating swing or the oscillating system. And due to this resistive force, the amplitude is going to decrease. So such type of oscillations are known as the damped oscillation. Suppose we want to make the oscillation of a swing continuous. So we have to apply the force by our leg. We have the experience. And this force applied by our leg on a swing, that is known as the periodic force. After applying the periodic force, what are the oscillation of a swing is known as the forced oscillation. Here we are going to discuss this thing about the damped oscillation and forced oscillation. Now first, what is the pure simple harmonic motion? If no any resistive force or the internal frictional force acting on a mechanical system to execute a simple harmonic oscillation. That means in absence of any resistive force or any frictional force, what are the oscillation take place of a system that is known as the pure simple harmonic oscillation. And we are first going to deal the differential equation for pure simple harmonic oscillation. So question is that define pure simple harmonic oscillation. And obtain differential equation for it. Differential equation for first the definition of pure simple harmonic oscillation. For that purpose, the definition is like this way. If no external force or internal frictional force acting on a mechanical system of the body to execute the simple harmonic oscillation. Such oscillation is known as pure simple harmonic oscillation. That means no any external resistive force or no any internal frictional force acting on a body which body perform the oscillation. So such oscillation of a body are known as pure simple harmonic oscillation. In pure simple harmonic such oscillations are in an ideal situation. There is no any resistive or internal frictional force. There is no any resistive or internal frictional force acting on an oscillating body or the oscillating system. So there is the information about the pure simple harmonic motion. Clear this thing? So there is the definition of pure simple harmonic oscillation. Now, how we obtain the differential equation for pure simple harmonic motion? For that purpose, at distance x or the displacement x, the staying force acting on a body is, because for simple harmonic motion, the staying force is important to act. Right? For that purpose, here, differential equation for simple harmonic motion. Differential equation for simple harmonic motion. SH. The staying force on a system at x displacement for simple harmonic motion is Fs is equal to minus Kx. Right? And if a solution of a system is A, then from Newton's second law, F is equal to m F is equal to ma. Equation number 2. Comparing equation 1 and 2. Comparing equation 1 and 2, we obtain ma is equal to minus L. But we know that acceleration is equal to dv by dt and velocity is equal to dx by dt. Already we discussed in chapter 3 and 4. Therefore, acceleration A is equal to d square x upon dt square. Substitute in equation 3. In equation 3, therefore, m into d square x upon dt square, m into d square x upon dt square is equal to minus k. Therefore, d square x upon dt square is equal to minus k by m into x. Therefore, d square x upon dt square is equal to plus k by m into x is equal to 0. But we know that k upon m is equal to omega square. Therefore, d square x upon dt square plus omega square x is equal to 0. Is the differential equation for pure simple harmonic motion. Simple harmonic. Here is okay. Now, to obtain the differential equation, only we compare the two forces. One is what is the resultant force act during the simple harmonic motion. Here we consider the pure simple harmonic motion. Therefore, only the restoring force act on an oscillating system or the oscillating body. Fs is equal to minus K. And due to this force, restoring force, the body performs the accelerated motion, and if the acceleration is A, then from Newton's second law, F is equal to mv. Now we compare these two forces. Therefore, ma is equal to minus K. A is the acceleration. Acceleration is the derivative of velocity with respect to time, and velocity is the derivative of displacement with respect to time. Therefore, A is equal to dv by dt is equal to d by dt as it is. Now we substitute the value of v. V is equal to dx by dt. Therefore, d into dt square x upon dt square, that is known as double derivative of displacement with respect to time. Already we discussed this concept in chapter 3 to obtain the equation of acceleration. Substitute this value of acceleration in equation 3. Therefore, m into d square x upon dt square is equal to minus kx. Therefore, d square x upon dt square is equal to minus k upon m into x. Therefore, d square x upon dt square plus k by m x is equal to 0. But we know that omega is equal to under root of k upon m. Therefore, k upon m is equal to omega square. Right? And also we know that the k is equal to m omega square. Okay. Substitute here. Therefore, d square x upon dt square plus omega square x is equal to 0. So, it's the differential equation for pure simple harmonic motion. So, keep in mind that in differential equation, whatever the term has the higher power of differentiation must be alone. No any multiplier required. And due to that reason, first we divided each term by m. Clear? So that is the differential equation for pure simple harmonic motion. The same method we have to obtain the differential equation for damped oscillation and forced oscillation. In damped oscillation, how many forces act? First, this force is at and also another is the resistive force react. Addition of these two forces we have to compare with the F is equal to M. Okay. After that, we are going to discuss about the damped oscillation. Now just we did a differential equation for pure simple harmonic motion. But this type of the oscillation take place in ideal situation because all the system oscillate in some medium, that means the fluid. Fluid, that means the substance which can flow, that is known as the fluid. Air medium is also known as the fluid medium, water medium, all are the fluid medium. Any oscillation always take place in any present medium. Therefore, the resistive force is always acting on oscillating system or the oscillating body. So pure simple harmonic motion or the oscillation does not exist. Right? Okay. So that is the ideal situation. Now we are going to discuss about the damped oscillation. So when any body or the system is oscillating in a medium, at that time in some type of the resistive force is acting on a body. The resistive force is directly proportional to the velocity or the speed of oscillating body. We have the experience as we walking on a road, we feel the resistance by the air medium is less compared to the going on a bicycle or the bike. As we ride a bicycle, the resistive force by the air medium is more compared to the walking. Right? That means as the speed of the body, or that means the person or the oscillating system increases, so resistive force is also increased. Therefore, here in oscillation, due to the resistive force, the amplitude of oscillation continuously decreases with time. Such oscillations are known as the damped oscillation. Such oscillations are known as damped oscillation. First we define it. And after that, in damped oscillation, here the two forces we consider. One is the restoring force, second is the resistive force. Clear? Okay. First we are define damped oscillation. For damped oscillation, the oscillation in which the amplitude of a system decreases with time. Decreases with time. Such oscillations are known as damped oscillation. So there is the definition of the damped oscillation. Again, the oscillation in which the amplitude of a system decreases with time. Such oscillations are known as the damped oscillation. In damped oscillation, the resistive force act on a system is directly proportional to the velocity of a system Therefore, resistive force FD directly proportional to the velocity and also in opposite direction of velocity. Therefore, FD is equal to minus B into V, where B is known as, there is actually the proportionality constant, B is equal to constant. It is known as damped coefficient. Damped coefficient. Here is, so from this equation, B is equal to FD upon V. SI unit of damped coefficient. SI unit of B. Damped coefficient is Newton second per meter, and dimensional formula of damped coefficient is B is equal to Newton M1 L1 T minus 2 into T1 upon L1. So it's equal to M1 L0 T minus 1. There is the dimensional formula of damped coefficient. So frequently this portion is asked in 1 mark objective question. One marks objective question. Dimensional formula of the SI unit. SI unit is from dimensional formula kg per second. Kg per second. Here is okay. Now, damped coefficient is depends on types of medium and shape and size of the body. Damped coefficient is depends on types of medium and shape and size of a body. So there is the information about the damped oscillation and what is the damped coefficient. Again, what is the damped oscillation? The oscillation in which the amplitude of a system decreases with time. Such oscillations are known as the damped oscillation. Okay, during the damped oscillation, the resistive force F on a system is directly proportional to the velocity of a or the speed of a system, and also in opposite direction. Therefore, resistive force Fd proportional to minus V. Therefore, Fd is equal to Bv. B is the constant. It is known as the damped coefficient. Now, so from this equation, the B is equal to Fd upon V. SI unit of damped coefficient is Newton second per meter or kg per second. And dimensional formula of damping coefficient is B is equal to M1 L1 T minus 2 T1 upon L1. That means the M1 L0 T minus 1. Now we are going to obtain the differential equation for damped oscillation. Right? The system or the resistive force the strain force F on a system for displacement x is Fs is equal to minus kx, equation 1. And additive force FD is equal to minus BB, equation 2. Therefore, total force act on a system in damped oscillation is F is equal to Fs plus Fd is equal to minus Bv minus Kf. Equation, right? Okay. If the acceleration of a system is if the acceleration of a system is then from Newton's second law, F is equal to m. Equation number 4. Comparing equation 3 and 4. Comparing equation 3 and 4. We obtain m at, or the m is equal to minus dv minus l. Now substitute v is equal to dx by dt and acceleration is equal to d square upon dt square. Therefore, m into d square x upon dt square minus is equal to minus b dx by dt minus kx. Therefore, m into d square x upon dt square plus b into dx by dt plus kx is equal to 0. So it's the differential equation for damped oscillation. For damped oscillation. There is a differential equation for damped oscillation. Here? Okay. Now, the same method we obtain the differential equation. But here, the one additional force is the additive force. Again, during the damped oscillation, the additive force act on a system for displacement x is Fs is equal to minus kx. And additive force Fd is equal to minus b. Therefore, total force act on a system in damped oscillation is F is equal to Fs plus Fd is equal to minus dv minus kx. If the acceleration of a system is a, then from Newton's second law, F is equal to ma. Comparing equation 3 and 4, therefore we obtain ma is equal to minus dv minus kx. Here we know that velocity is equal to differentiation of displacement with respect to time, and acceleration is equal to double derivative of displacement with respect to time. Substitute here, therefore m into d square x upon dt square is equal to minus b dx by dt minus kx. Take this negative term on left hand side, therefore m into d square x upon dt square plus b into dx by dt plus kx is equal to 0. So that is the differential equation for damped oscillation. Clear? Now, what should be its solution? Solution, that means we substitute the value of x. So this value of x satisfies this equation. That is known as the solution of a differential equation. Clear? Okay. Now just read here the differential equation for damped oscillation is, again we write down here, differential equation for damped oscillation is m into this square x upon dt square plus d into dx by dt plus kx is equal to 0. That is our damped oscillation. Now the solution of this damped oscillation is the solution of such differential equation is xt is equal to a raised to minus bt upon 2m into cos omega dash t plus phi. Omega dash t plus, that is the differential equation of damped oscillation, right? Where at is 1, at is equal to a raised to minus bt upon 2m is the amplitude force, is the amplitude of damped oscillation. It is decreases with time. It is decreases with, and omega dash is angular frequency omega dash is equal to under root of k upon m minus b square upon 2m whole square, or the b square upon 4m square, b square upon 4m square. So these are the constant. That is the amplitude and that is the angular frequency of the damped oscillation. The graph of displacement versus time for damped oscillation is, now we do the graph of displacement versus time for the damped oscillation. So graph is this manner. The amplitude is continuously decreases with time. This way. There is the amplitude at time t is equal to a raised to minus bt upon 2a. Here we consider the displacement xt along the y-axis and time t along the x-axis. There is the x is equal to 0 position, and there is the x is equal to minus a, and that is corresponding to the x is equal to a position. The same way here the displacement is continuously decreases with time. Parabolic. Clear? And here the initial phase phi is equal to 0. Phi is equal to pi by 2. Because its oscillation is started from the x is equal to plus a position. So there is the graph of the displacement versus time for the oscillation.